There is no ideal place to detonate a nuclear bomb. In any scenario, its use leads to severe consequences. However, some locations make such an explosion particularly catastrophic, one of them being outer space. This might come as a surprise, since space is vast and mostly empty, but what could possibly go wrong? The United States has a brief yet eventful history of testing nuclear weapons in space. During the early years of the space race and at the peak of Cold War tensions with the Soviet Union, from the late 1950s to the early 1960s, scientists and military strategists explored the potential advantages of detonating nuclear bombs high above Earth. These benefits were considered from both defensive and offensive perspectives. From a defensive standpoint, a nuclear explosion in space could act as a shield against a Soviet intercontinental ballistic missile (ICBM) attack. When a nuclear bomb detonates, it generates an electromagnetic pulse (EMP) and releases a field of highly charged electrons, which can severely damage electronic devices, including the guidance systems of long-range missiles. Unlike airplanes that fly across the ocean, ICBMs travel like rockets, first ascending through the atmosphere, then crossing into outer space before descending toward their target. If they were to pass through an intense field of electromagnetic interference, their electronics could be disrupted or disabled, making them ineffective. There was also an offensive rationale for detonating nuclear weapons in space. By the late 1950s, scientists had confirmed that Earth possesses a powerful magnetic field originating from its core. The inner core consists of solid iron, while the surrounding outer core is composed of free-flowing liquid metal. This movement generates a magnetic field that extends from the Earth's interior far into space, forming a series of circular magnetic field lines that flow from the southern hemisphere to the northern hemisphere. These layers of magnetic fields act as a protective barrier, trapping highly charged radioactive particles from the sun and preventing them from reaching the Earth's surface. This shielding effect is one of the key reasons life exists on our planet. So, in a way, we have magnets to thank for that. We can observe the effects of Earth's magnetic field when some of the charged particles it captures are directed along its field lines and enter the sky above the North Pole, creating the phenomenon known as the Northern Lights. A thermonuclear explosion, in essence, mimics the process of forming a miniature sun. If such an explosion were to occur within Earth's magnetic field, the outcome would resemble the interaction between the real sun and the planet's magnetic shield. The highly charged radioactive particles released would become trapped and follow the magnetic field lines. While the outer layers of this magnetic field would guide the trapped particles toward the North Pole, the lower layers would direct their electromagnetic energy toward lower latitudes, potentially targeting regions such as the Soviet Union. Understanding this concept is crucial to comprehending why anyone would consider detonating a nuclear bomb in space. The primary concern isn't the explosion itself, but rather the electromagnetic aftereffects and their interaction with Earth's magnetic field. Theoretically, a strategically positioned thermonuclear detonation over the Indian Ocean could release an electromagnetic pulse, EMP, that, once caught in Earth's magnetic loops, would be directed toward the Soviet Union's missile defense systems. This could disable their electronic infrastructure, rendering their defense mechanisms ineffective and leaving them unable to detect or respond to a long-range nuclear strike. However, the only way to test these theories was through real-world experimentation, by detonating a nuclear bomb at high altitudes and observing the results. Given that this was the late 1950s, conducting live above-ground nuclear tests, despite their immense power and risks, was a common practice of the time. Between April and August 1958, the U.S. military carried out a series of 35 nuclear tests under Operation Hardtack. These tests were conducted in what the government referred to as the Pacific Proving Grounds, a collection of tiny islands in the central Pacific Ocean that are so obscure most people wouldn't even know they exist. In fact, you'd need to zoom in at least 10 times on Google Maps just to see them clearly. Among these nuclear experiments, 3 were specifically designed as high-altitude tests. The first of these, codenamed Yucca, involved attaching a 1.7 kiloton nuclear bomb to a hot air balloon and sending it into the upper atmosphere. While this method may sound risky, and it certainly was, the military had spent 2 years preparing for it. They had already deployed 76 test balloons before finally proceeding with one carrying a live nuclear device. The Yucca test was launched from a U.S. aircraft carrier near Bikini Atoll on April 28th. The balloon was released at 11:25 a.m., reached its target altitude of 85,000 feet by 12:50 p.m., and detonated at 2:40 p.m. The primary objective of this test was to measure the strength of the electromagnetic pulse, EMP, produced by the explosion. Scientists had theorized that an EMP generated at high altitude would be significantly stronger than one from a ground-level detonation, but they lacked precise data. The test results confirmed that a high-altitude EMP could be over 1,000 times more intense than the same explosion at a lower altitude. While this revelation was alarming, it was precisely the outcome the military had hoped for, so they proceeded with further tests. The next experiment, Teak, aimed to push the boundaries even further. Instead of a balloon, the bomb would be launched using a Redstone missile, and the explosive yield would be significantly increased to 3.8 megatons. The location for the next test was moved to one of the most remote outposts controlled by the U.S. government, Johnston Atoll, a small island located west of Hawaii, about as close to the middle of nowhere as one can get. The test, codenamed Teak, was launched at 11:47 p.m. on July 31st. The warhead detonated at an altitude of 76 kilometers, 43 miles, not technically in space, but still incredibly high. Unfortunately, the missile's guidance system was not programmed correctly, causing it to explode directly above Johnston Island, instead of further downrange over the ocean as planned. The result was a blinding nuclear fireball, creating what appeared to be a miniature sun within Earth's atmosphere. The explosion was so intense that it was visible from 800 miles away in Hawaii and remained in the sky for nearly half an hour. The thermal radiation was strong enough to give military personnel stationed on Johnston Atoll sunburns, despite it being nighttime. Beyond the visible effects, the detonation also disrupted high-frequency communications across the Pacific for 8 hours, demonstrating just how powerful a nuclear explosion at high altitude could be. Given the shocking results of Teak, the U.S. military decided to conduct a similar test, codenamed Orange, on August 11th. This time, another 3.8 megaton bomb was launched on a Redstone missile, but the explosion occurred at a lower altitude, 43 kilometers, 27 miles. The results were far less dramatic. The explosion was only visible in the sky for about 5 minutes, and it did not cause the same level of communication disruption as Teak. These tests confirm that altitude plays a crucial role in the effects of a nuclear explosion, particularly regarding its electromagnetic fallout. The next step? It would take a few more years of planning before the U.S. military was truly ready to detonate a nuclear bomb in outer space. That moment finally arrived in 1962 with Operation Fishbowl, coinciding with the same year as the Cuban Missile Crisis, which nearly led to the end of human civilization, probably just a coincidence. However, Fishbowl was more than just another act of Cold War nuclear escalation. It was a joint effort involving the U.S. military, the Atomic Energy Commission, and the Defense Atomic Support Agency, aimed at further studying high-altitude electromagnetic pulses, EMP, the interaction between nuclear radiation and Earth's magnetic field, and the impact of such detonations on radio communications. The Fishbowl tests were closely monitored by a vast network of observation stations, both on the ground and in the air, across a wide region surrounding the planned detonation sites. Additionally, monitoring extended to the Samoan Islands in the southern hemisphere, an area referred to as the Southern Conjugate during these tests. Scientists hypothesized that fallout from an explosion over Johnston Island in the northern hemisphere could be carried along Earth's magnetic field lines to Samoa in the southern hemisphere, potentially creating an aurora that would visually link the two island regions. Here is the paraphrased version of the fourth part of the text without bold formatting. Looking at the actual results of Operation Fishbowl, the success rate was inconsistent. Some tests achieved their objectives, while others were complete failures. It's surprising just how often these nuclear experiments went wrong. Frankly, it's remarkable.